The tires of a bicycle have radius 13 inches and are turning at the rate of 215 revolutions per minute. How fast is the bicycle traveling in miles per hour? Okay, so this is an interesting application of angular velocity, in particular in relation to the application of angular velocity with circular motion. And we're just focusing on special cases where the angular velocity is constant. So the angular velocity doesn't have to be constant, right? You could have like an angular acceleration, for example, but we're focusing on situations with constant angular velocity. And so this man is riding the bicycle. The tires have radius 13 inches, and they give us the rate at which the tires are turning in relation to angular velocity. So, you think angular velocity, that has to be like radians per second. No, it's any kind of rotation amount, an angle amount per time. Well, okay, revolutions, that's not an angle. Yeah, it's a form of an angle, because a revolution is an angle, right? When you think about a revolution, you're thinking about it's a full 360-degree rotation. That's what a revolution means. So the term revolution that's an angle. One revolution is 360 degrees. One revolution is 2 pi radians. So this is an angle per a certain amount of time. Any time you could do revolutions per year, per decade, whatever. That's an angular velocity. So it gives us the radius of the tires, the bicycle tires, and their angular velocity. And with that, it wants us to answer how fast is the bike traveling in miles per hour. Okay, so probably the main question is, well, how do we know how to deal, we learn how to deal with the circular motion system. There's arc length S, radius R, there's angle theta, angular velocity omega, speed, time, right? So we already worked problems in previous videos where we were given some of these parameters and we solve for the remaining parameters. So we can do that now, but how does that translate to how fast the bicycle is traveling? Like, what do we need to solve for? Well, if you think about it, it's really how fast the bicycle is moving is going to be how fast the surface of the tires are moving. Not rotating, but how fast what their actual velocity is, like speed is, in terms of change in position per time. And you can think about intuitively why that's the case. And unless the tires are slipping. If they're slipping, then that's not the case. But assuming they're not slipping, then however fast the surface of the tires are moving from a change in distance with respect to time, a pure velocity standpoint, that's how fast the bicycle itself is going to be moving. That's how fast just the man on the bicycle is going to be moving. Okay, so what we're solving for then is V. We're looking at, this is just, each tire is just in normal circular motion. I think the technical term for that is uniform circular motion. We're thinking about a constant angular velocity. So he's like, this coasting down the path or the road. So it's the same system that we've been working with so far. We just need to solve for V. That's it. Okay, so when solving for V, we want to be in radians, right? Because radians are unitless, and we're trying to get to, if the omega here is in radians per time, then all we have to do is multiply by a distance, and we'll get distance per time. That's velocity, right? But we're not going to go to radians per second because we're trying to get to miles per hour. So we're going to actually convert this to a rotation. We're going to do radians per hour. So, okay, we know that the omega of the tires is 215 revolutions per minute. Okay, so we can easily get minutes to hours. We'll say that we know that there's 60 minutes in 1 hour. Okay, so now we're in, if we take 215 times 60, that's going to give us the omega of the tires in revolutions per hour. Okay, but we want radians per hour. So how do we convert to radians? Well, that's easy, because we know that for every 1 revolution, that's equivalent to 2 pi radians. So now we're in radians per hour. 215 times 60 times 2. And we can just leave this in terms of pi until the end. So 25,800 pi radians per second. Okay, now how do we go if we have omega and we're trying to get to velocity? How can we get there? Well, there's no need to memorize these formulas. I'm going to say that over and over again. You just, okay, so with uniform circular motion, write out what you know. We know that S is equal to r theta if we're dealing in radians. Okay, the omega is the angle with respect to time. The velocity it's the arc length with respect to time. And so now you can just play with these to get whatever relation you need. And the first thing you could do is just S is r theta. Now theta divided by t is omega, so r omega. So you have v is equal to r omega. You could do, so there's S divided by t is equal to r omega. There's another equation. You could play with this, solve for S, solve for t, whatever, right? You could find anything you want. As long as you have certain parameters to start with, you're going to need some information, right? You could solve for whatever you want. So we've got omega and we've got r. So v is equal to r omega is that's perfect. So r is 13 inches. Omega is 25,800 pi, and radians is unitless. So this is, let's see, 13 times 25,800. 335,400 pi, and this is inches per second. So that's how fast the bicycle is traveling. 335,400 times pi inches per second. But that's not very intuitive, right? If you told somebody that's how fast you were going, that's kind of silly. You have no idea what you're talking about. So that's what we do. We convert units, and for presenting them to people, we convert them into the units we need. So, okay, we need to get to, oh, wait, no, I'm sorry. This is radians per hour. Yeah, we converted it to hours. Radians per hour. Yeah, we're already in hours. So it's this many inches per hour, which is still not very intuitive. Okay, so 335,400 pi inches per hour. Okay, so what we're going to do is we just need to convert inches to miles. So that's, unit conversions are easy. Okay, so they give us a unit conversion here. We could have easily looked this up. So we know how many feet are in a mile. So we need to let's start by getting to feet. How many inches are in a foot? Well, there's 12 inches in 1 foot. So now we're in feet. So we use this conversion. There's 5,280 feet in 1 mile. And there we go. Now we're in miles per hour. Okay, so we take this times pi divided by 12 divided by, okay, so now we can just go ahead and evaluate this with get rid of the pi, 16.6 miles per hour.